Alright, so this is meant to be your walkthrough for projectiles at angles. This is the stuff that we worked on at the end of class over the last several days. Honestly, just as a quick little intro, given everything that's going on, we are going to, for the most part, stick primarily to this way of solving our projectile problems when they're done at angles. Horizontally launched projectiles we've done quite a bit of, several examples of, so I might go forward with those steps for 1 and 2 or backwards, kind of like I did in number 5 on the homework from the other day for assignment 3. But for projectiles at angles, because we have so little class time now that Monday got canceled and all of that fun stuff, in this particular video I'm sticking in how I'm going to approach it on the exam. At the very least, it's going to be very much straightforward, very similar to what we're doing here. So this is just meant to be a quick overview of the equations that we should use. I'll briefly mention why we should use those equations, but I'm not going to go into nearly as much detail as I did in class. So if you're more curious, please don't hesitate to ask. But at the very least, you'll get the equations you need, the order you need to do them in, and why we're doing them that way. That's meant to be the goal here. So we have a projectile of some kind being fired. In this particular case, we've got a cannonball that is being shot across, I don't know, probably a field, right? Probably Napoleon, crazy little guy firing his cannons at Russia. Never invade Russia in the winter. Should have been something he learned the hard way from, or learned from other people trying it the hard way, but whatever. It's cool. So we've got ourselves a cannon. In this particular example, what I do want you to recognize is that the cannon is going to travel up some measurable distance, reach a point where it stops traveling up, and then travel all the way back down. And this is going to be very, very, very similar to the other problems that we had done literally just in the last unit, where we had thrown something up into the air. It slowed down, came to a stop, turned around, and come back. And all we've done now is add some measurable horizontal distance in between those two, starting and ending points, and that's really all it is. So we still have the same overarching idea in that in this particular case, the y-axis, gravity, is still what determines how long this ball is in the air for. This cannonball, tennis ball, football, baseball, softball, whatever, it determines how long the ball is in the air. That's what gravity does. So we're still going to treat this as either a drop problem or, in this case, a throw-up problem, the same as we always did. And once gravity has pulled it out of the air, it can no longer move left and right. So the goal number 1, still step number 1, is to find out how long it's in the air using gravity. Then we know how long gravity allows it to move left and right. And it's still going to be the exact same scenario. Now, the only exact same scenario, I should say, is horizontally launched projectiles. The only difference here is that this cannonball, or these projectiles at angles, obviously are launched at angles. And so you're going to wind up with a triangle. And the hypotenuse of that triangle is going to be the initial vector that you're being given. So in this case, we were given a velocity of 60 meters per second. That velocity of 60 meters per second is our hypotenuse of this little triangle that we're going to be making. And you'll notice that there are the other two sides of this triangle. Both of those sides represent something. So just like we started doing way back at the beginning of the year, back in Unit 1 when we were doing some vector resolution stuff, the horizontal component, because this was a 60-degree angle as well, the horizontal component of this triangle represents the horizontal component of that 60 meters per second, right? Not all of that 60 meters per second was launched horizontally. Not all of it was launched vertically. A fraction of it went left and right, horizontal, independent of gravity. Gravity doesn't care about that horizontal speed, but then there is part of it that gravity does care about, and that's my vertical component to this velocity, Vy. So if I'm looking to solve for either of these two components, right, we've got a first step is resolve our vector, and you'll see that on the front cover page of the unit packets that I gave you guys. The first step is to resolve the vector and find what Vx and Vy both are, because they're independent of one another. Vy right here is going to be influenced by gravity. Vx right here is not influenced by gravity, because gravity does not, never will, or at least never has, for thousands of years. So it's a pretty good trend. Never going to work in any direction other than up and down, right? It's not going to work left and right, north, south, east, or west. It always works up and down. So if you're interested in solving for the x horizontal velocity, right, your Vx value, your equation for Vx is always going to be the same. It's always going to be the velocity that was given to you, right here, your 60 meters per second, multiplied by the cosine of your angle. And again, the angle that we always use is given the variable theta. It's like x, but for things measured in degrees. And that's all that means. This is always going to be the equation that you should use to find your horizontal component. It's because this Vx technically is the adjacent side to that triangle, to that 60 degrees in that triangle, and your hypotenuse, obviously, is at 60. So if we plug in everything that we know, you get your 60 meters per second multiplied by the cosine of your angle, which was 60 degrees. Type that in your calculator. Make sure your measurements, your calculator is set 2 degrees, not to radians, and you should get a horizontal velocity of 30 meters per second. I'll write it right here so that it's right next to the number. Your horizontal velocity is 30 meters per second. Now your vertical velocity is going to be the exact same equation with one small but very important distinction. And that is that we're not using cosine, we're using sine, because Vy is on the opposite side of that triangle from my 60-degree angle. So we have to use sine instead. So in this particular case, it is the exact same setup. We have 60 meters per second is multiplied by the sine of 60 degrees. And then that is going to be equal to approximately 52 meters per second. I think it was actually 51.96. But being the monster that I am, I'm just going to round it. Now that we have both of these values, our horizontal component of that 60 meters per second and our vertical component of that 60 meters per second, I want you to go back up to the top and never, ever, 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 ever go back to using 60 or 60 again. We're done with them, right? We use that 60 meters per second at 60 degrees in order to find the horizontal and vertical components. Now we're going to take that vertical component and figure out how long it will be in the air for. That is still the first and actually primary goal with all of these projectile problems, is how long is this thing going to be in the air? We know that our initial velocity in this y direction is going to be a positive 52 meters per second. We know that our final velocity in this y direction is going to be a negative 52 meters per second, right? Because if we look at this, just like our vertically launched projectile problems, it's going to leave the ground with some measurable vertical speed, and then when it returns to the ground, it's going to return with that same measurable vertical speed. The only difference is the direction that that thing is traveling. That was really it. Your acceleration in your y direction only is 10 meters per second squared. So from there, there's no mention of distance, no measurement given to you in meters and meters alone. So knowing that that isn't part of your list of variables, lists of things that you can use in your equations, there's only one equation that fits the list of variables that we have, and that is Vf equals Vi plus At. Plug in what you know. Negative 52 is equal to positive 52 plus negative 10 multiplied by time. Now negative 10 is a function of time. As time changes, so too will be what you're adding and or subtracting in this case, because it's a negative 10, to that 52. So we've got to subtract both sides by 52 first. That's a step that some of us are forgetting on that last unit exam, and I don't want that to be a thing again this time. So you get negative 104 is equal to negative 10 multiplied by time. From here, divide both sides by negative 10, and you get yourself a time of positive 10.4 seconds. And that's fantastic because you can never have a negative measurement of time. That is how long gravity will let this object be in the air. Just like we did for our drop problems in our horizontally launched projectile problems that we were working on, right? You start it with a drop equation because that's how long gravity lets it be in the air. Well, in this case, you're throwing it up into the air, and gravity is still the thing that determines how long it's in the air. Once you know how long it's in the air, you can bring it on down here to the horizontal component, and if you know the amount of time it's allowed to be airborne for is 10.4 seconds, and the horizontal velocity that it was traveling that direction in basically was 30 meters per second, right? That was my horizontal velocity. I'm going to bring it all the way down here, put a box around this so that you guys know why I chose the 30 instead of 60 or 52. This is my horizontal speed. I can find the range of this projectile. dx is equal to vx multiplied by t. Dx, in this case, my horizontal distance is equal to 30 meters per second multiplied by 10.4 seconds. And we should get a range for this particular projectile of 312 meters. So what you're going to be asked to do on the exam, or even just in the review, at the end of the unit packet that we're working in right now, is going to be these particular steps. You've got to resolve that vector. You've got to find out how long it's in the air with the vertical component of that vector, and then you've got to, using the horizontal component of that vector, find out how far it can go in that amount of time. Let's do something similar. We've got Evelyn building a giant slingshot in order to throw water balloons at her friend Hank. This is an obnoxiously large slingshot. If anyone built something like this, I would legitimately be impressed. But the scenario is still the same, right? Hopefully we're sending water balloons. It looks like Evelyn is sending Hank here. I'm not asking questions. I'm not paid enough to ask those questions, right? But we still have a 45-degree angle. We have a velocity that this is being launched at of 40 meters per second. It's going to go up, reach some velocity where it runs out of vertical speed, just like our throw-up problems did, and then it's going to come back down and return to the ground. So we can set this up just like we would have any other triangle, and we can resolve this 40 meters per second, right? That was the velocity that they gave us at 45 degrees. And we can find from that our horizontal component to that speed, and we can find from that our vertical component to that speed. So that is your step number one for your projectiles at angles. Always step number one. Let's solve for y first. We have Vy is equal to velocity multiplied by the sine of theta. In this case, Vy is equal to my initial velocity of 40 meters per second multiplied by the sine of 45 degrees, and we should get a horizontal velocity, sorry, in this case vertical velocity of, I believe the answers were down below on the next page, sorry, 28, yeah, 28.3. That is what our velocity should work out to be, 28.3 meters per second. That is your vertical speed. And that is the speed you're going to use down here in letter C, because the vertical speed is what gravity works against, and that is what will determine how long this water balloon can stay in the air. Vx for our x direction is equal to v multiplied by the cosine of theta. That is the only difference between these two equations. It is important to remember sine goes with y and cosine goes with x. But beyond that, I mean, they're the same basic equations. They're the same process for solving them. Sorry, it is not 60. That was the last problem that we did. We have still 40 meters per second multiplied by the cosine of our 45-degree angle, and check it out. When you plug this into your calculator, you will get the exact same value. Now, don't panic right off the bat. Think to yourself, why does this make sense? Why should my horizontal velocity be the exact same as my vertical velocity, despite the fact that I should use both of them in different places? It's because of the angle that we had. This is a 45, 45 right triangle. And from your geometry classes, your algebra classes maybe even, 45, 45, 90 right triangles have two sides, two legs that are the same length, right? Equidistant. No, it's the same distance away from each other. They're both the same length, right? And that's the main idea. So, not the end of the world. Yes, in this one particular case, because it was a 45-degree angle, both of those wind up being identical. So, how long will it take it to hit the ground? It is still the exact same scenario that we had done before in the last problem. Vf equals Vi plus At. We have negative 28.3 is equal to positive 28.3 plus negative 10 multiplied by our time. We have to subtract 28.3 from both sides, so 28.3, that's 40, 56.6. So we get a negative 56.6 is equal to negative 10t. Divide both sides by negative 10, and you get 5.66 seconds total in the air. That is the amount of time it spends in the air. Now that you know the amount of time it spends in the air, you can plug it into Vx multiplied by t. It's the same procedure, the same steps each time. So we got horizontal distance of 28.3 multiplied by 5.66 seconds. This one I cannot do in my head, so 2d should give us a value of 160. Oh, sorry. How long did it take it to land on the ground? That's what it was. We used this all the way down here. I skipped a step. Alright, well now I'm embarrassed because this is recorded, but also I'm really far into the recording and I'm not good enough at YouTube to go back and edit. So what I did was I calculated, and let's try this. I'm going to live life on the wild side. Try the lasso tool. Can I... Oh, look at me. It's almost like I knew what I was doing. So let's do that again. Because this whole process here was for finding the total amount of time that the thing was in the air for, which is great. But this first one, they asked me how long did it take to reach the highest point. Pretty silly of me, but that's totally okay. It's super late at night when I'm making this. If you want to find out how long it's going to take to reach your highest point, you have to remember what your velocity is at that highest point. And your velocity at your highest point, your vertical speed at your highest point, is always 0. That was from our last unit, right? Your vertical speed at the very top is always going to be 0. And if your vertical speed at the very top is always going to be 0, then 0 is equal to, again, positive 28.3 plus negative 10 multiplied by time. Notice the only thing that changes is my final speed. So I still subtract 28.3 from both sides. I get negative 28.3 on this side is equal to negative 10 t, right? 28.3 and 10 still are not like terms, so I cannot combine them. Now I divide both sides, and I get a time of 2.83 seconds to the top, to the highest point, which you'll notice is exactly half the total time, because it has to go to its highest position and then fall all the way back down to its lowest position. So technically C and D, while on the exam you're not going to be asked to do this both ways, you could solve for total time in the air using either C or D. It's entirely up to you. If you like using one of the velocities at 0, recognize it's only 0 when it is at its highest point in its trajectory. And if you want to skip all of that, because at the end of it you'd have to double that, if you want to skip all of that, just recognize that your initial velocity up and your final velocity back down are the same value. One of them has a negative. All right, the velocity coming back down has a negative. So in this case, it's only going to go, what did that work out to be? 160-ish meters is what that was. So no, this is not going to reach Hank. It's going to be 15 meters shy of Hank. There are going to be a number of things that you could do in order to extend your range. You could increase the amount of time that it's in the air. To increase the amount of time that it's in the air, you would have to increase potentially, and actually this is what your gizmo that should show you. You could increase your initial vertical direction in that y direction, right? So either send it with a larger velocity vector right here, because 45 is actually the one that's going to give you the best. So send it with a larger velocity vector right there, or send it with a larger horizontal velocity vector so that it covers more distance in that short amount.